Day 6, session number 13, topic battery construction and battery management system. Today's expert speaker, Mr. Chinmay Gore sir, is a dynamic entrepreneur and industry professional with over a decade of experience in manufacturing operation and electrical vehicle technology. He is the founder and director of Yogitech Industries Private Limited and Yogitech Batteries, a startup engaged in the development of supply of electrical vehicle batteries and components, where he has been leading innovation and manufacturing innovations since 2018. With a strong academic background that include a BTech in civil engineering from Virgin College of Engineering Sangli and MBA operation from Wilker Education Mumbai. He brings a unique blend of technical experts. His professional strength include project and operation management, supply chain and purchase decisions, cash flow management, and hands-on experience with tools such as AutoCAD, SolidWorks, along with programming Python. Known for his passion, leadership, and ground-level management skill, Mr. Gore offers valuable industry obtained insight, particularly and involving domain of electrical vehicle technologies and manufacturing. Thank you, Gore sir, and I'm request to start your session.
Thanks a lot. I need to share my screen. If you could
Yes,
enable.
yes.
I'm not able to present right now.
So please check.
Yeah.
Okay, this thing is visible.
Yeah.
Yes.
Can you hear me?
Yes.
All right. And I hope everyone can see the screen.
Yes.
Yeah, perfect. So I hope everybody is familiar with batteries, lithium-ion batteries, and to start with, I hope everybody is comfortable with English, Marathi, and Hindi.
Sir, English.
Okay, English. So let's start with
Or mix
battery.
with Hindi, no issue.
Sorry.
Sir, there is
Or
a
mix with
background
Hindi,
sound.
no issue.
Yeah. All right. Great. So my name is Chinmay Gore. I'm a founder of Yogitech Industries Private Limited. I've been working with batteries since last 10 to 12 years. I started with electric two-wheeler batteries. Now we supply batteries to more than 180 happy customers. We do batteries for lithium ion, lithium ferrophosphate, lithium titanate oxide, NMC, NCA, and all other types of lithium based technology. We make batteries for electric two-wheelers, e-rickshaws, government automation projects, solar street light, and material handling equipment. And we make batteries from 3 volt to up to 1000 volt. So for that domain knowledge, I'd like to start with the basic definitions of batteries so that we understand it correctly, and the technicalities won't be lost on us. So the batteries basically are energy storage devices, nothing else. In batteries, we store the energy in terms of chemical energy. When we charge the batteries electrically, the batteries get charged, and the storage of energy happens in chemical form. So that's what we call electrochemical oxidation reduction. And for the history, it started with we as Indians want to believe that it started with Rishi Agastya. Then in the 16th century, Alessandro Volta came in from Italy. That is what documented. And in 1800, Leclanche नावाचे गृहस्थ एक होते ज्यांनी बॅटरीज मध्ये बॅटरीचं इन्व्हेन्शन केलं असं आपण म्हणू शकतो. सो हे जे लेक्लांच आहेत फ्रेंच माणूस, त्यांनीच लिथियम बॅटरीजचं पण पायोनियर आपण त्यांना म्हणू शकतो. अँड त्यांची अजून ही कंपनी आहे लेक्लांच नावाची, जी लिथियम टेक्नॉलॉजी विकते. भारतामध्ये पण काही त्यांचे प्रोडक्ट्स ते विकतायत. दॅट बिंग सेड, बॅटरीज सगळ्यांना माहिती आहे कुठं कुठं वापरले जातात. होम, इंडस्ट्रीयल, मेडिकल, मिलिटरी, एज्युकेशन, टेलिकॉम आणि इतर बरेच त्याचे ॲप्लिकेशन्स आहेत. आणि ज्याच्यामध्ये टिपिकली
Can you speak in English only?
या ओके, perfect. Thanks for feedback, and I hope feedbacks should be regular. थोडंसं let's make it interactive, right?
Hello, sir.
Yeah,
Sir, sorry, sir. Maximum participants in out of Maharashtra. Okay, that's
Great.
please.
no issue. So what we'll do is the applications, as you can see on the screen, home, industrial, all the applications that we know of the batteries. And typically every battery, even though the technology is similar, the base technology is similar, every application requires different types of batteries. The chemistry differs, the BMSs differ, the way the battery is built, that also changes according to what the battery is used for. For example, if there is a telecom requirement, the battery specifications are completely different compared to some home applications or medical applications. The enclosure changes, the way the battery is assembled, the type of welding, the type of assembly process that is followed changes drastically. So that is the one of the things. That again, alternative storage solutions are also available. Combined with batteries, people use a lot of other applications like hydraulic and pneumatic. That is also a part of storage unit, like compressed air and other things. Let's come to lithium batteries. Typically, lithium batteries are better in efficiency is because of the ion that carries it from anode to cathode while discharging. Usually what happens in traditional batteries like nickel cadmium or lead acid batteries that were used to be the industry standard, what used to happen is within the battery, as you can see on the left hand diagram, within the battery, while discharging, the cathode, the electron used to travel from cathode to anode. And here what is happening is the positively charged ion is traveling from anode to cathode, which efficiently transmits from anode to cathode within the electrolyte. That's why the efficiency is higher. Usually, I don't know how many of you remember, there used to be a diagram where you used to have a circular motion of an electron, which was negatively charged. It used to travel circularly. Here, what is happening from, if you see on the top side, the electron is also traveling from anode to cathode, and the positively charged lithium ion is also traveling from anode to cathode. So this is the basics of how the battery works, and you can also see the similar type of thing happening on the right side while discharging, and also while charging, the process will reverse, right? So so the different types of lithium ion batteries, that is NMC, LFP, lithium titanate oxide, and all types of batteries, they change according to their anode. Usually the cathode remains the same or some form of carbon, and anode changes. The way the anode is composed changes. That's why the name changes of the battery. Like NMC is nickel manganese cobalt, NCA is nickel carbon and aluminum. And LFP is lithium ferrous phosphate. So that type of changes happen in lithium metal sites. So anode changes. So let's cover those types because that is important for designing the battery in terms of the application. So these are commonly used applications of the batteries. Yeah. Does anybody have a question or something? No. Okay. So typically these types of batteries are used. We'll just cover some of them, like four or five, so that these batteries are generally used. Typically used. I'll also cover the usage of the batteries. Lithium cobalt oxide is one of the batteries that has maximum specific energy. You can fit maximum power, maximum energy within a small volume or small weight. So typically where there is high discharge rate, for example for electric power tools, or let's say drones, these types of batteries can be used. Then comes lithium nickel manganese cobalt oxide, that is NMC, which has enormous applications. We use a lot of NMC batteries in our own factory as well. This comes under wide range of applications for EVs, ESSs, energy storage systems, large systems like container batteries. These types of cells are used. Common chemistry is 811 or 622. That is, those are the proportions. 811 is nickel, manganese, and cobalt ka proportions. So 8 nickel, 1 manganese, and 1 cobalt oxide. So that type of chemistries are used. This cell, why this is used widely? Because it doesn't cost that much to have maximum energy, maximum specific power, relatively safer than this cobalt oxide. The performance stays the same for major lifespan of the battery, and it is relatively easy for NMC batteries to predict their life. Most of mobile phone use some combination of NMC. Their SOC, that is state of charge, and SOH, that is state of health, is easy to predict. That's why this is also one of the things that we use large. Again, lithium ferrophosphate is one of very widely used batteries because of their safe nature. Uh, this doesn't have specific energy as much as the other two, but the specific power and lifespan is very good. That's why these are also now becoming popular, where there is a inverter or home application, or also some of the EVs have these kinds of batteries. You can see new Mahindra vehicles, the electric ones, they are also, those have these types of prismatic batteries, lithium ferrophosphate. Typically they have low voltages, 3.2 voltage per cell, and typical other NCA and MC, those have 3.6 or 3.7 volt per cell. That's the nominal voltage. Then comes nickel cobalt aluminum oxide, that is NCA. This was popularized by Tesla, Tesla Electric Motors, that is the EV company. These were the original cells, 21700 cells that were used in original Tesla vehicles. Then they shifted to some other chemistry that they developed for their own specific vehicle. But typically this was famous for their extreme efficiency and extreme energy specificity. Also they were relatively safe and very cheap to manufacture. So usually a car requires a lot of batteries, a lot of cells to assemble one vehicle. So the cost effectiveness and higher specific energy of these batteries were very useful for electric cars. Then comes the lithium titanate oxide, which is very expensive. The cost of these batteries typically are like more than 3 times of the other batteries that we discussed. But these can be charged very fast. Very high discharge can be achieved from these, but they are not typically high in specific energy or specific power. The performance is excellent. The lifespan of these batteries is typically more than 10 times of LFP or NMC batteries. Safety is also on a very higher side, but what happens is the cost is very high and the efficiency is very high. Some of the drones and some of high performance two-wheelers and high performance cars have used these types of batteries. but they are very costly. So maybe a few startups are there who are cutting edge technology for the batteries. They are using these types of batteries for higher discharge and quick charging. You might have heard in some ad or something like some vehicle is charging in 15 seconds, some vehicle is charging in 5 minutes. So typically these types of batteries are used in those vehicles where maximum charging has to be done within 5 minutes or something. Even the racing cars typically use these types of batteries. Yes. So these are some upcoming chemistries that we are seeing in the market. That is sodium ion. Everybody might have heard about this. With that, India wants to reduce the dependency of lithium. So everybody wants us to shift to sodium, but obviously it has some of its own challenges. Then solid state batteries is something which we are looking forward to in terms of electric vehicle batteries. Lithium air, lithium sulfur, and some combination of supercapacitor and lithium ion battery that we might see in the future in the market. This is a very interesting case study. If anybody wants to do some research, supercapacitors plus battery is a very interesting combination that people are working on. Next. So, does anybody have any questions in terms of the chemistries and why we are studying it?
Yes, sir.
Yeah.
High discharge is a good parameter, or high discharging, you said high discharging and something in previous slide.
Right. Typically, when I'm talking about high discharge, it is the capacity to discharge at a higher current. It's not that it discharges very fastly, but it has a capacity to discharge quickly so that it gives maximum power within a small amount of time. Like for drones or equipments that heavy equipments, drilling machine or some machines that require a lot of energy for very small time. So
Okay, thank you, sir.
yeah, if the application is allowing you, you must go for those high discharge types of batteries.
Thanks, sir.
Yeah.
Sir, then state of health will be affected or not?
Yes, obviously state of health will be affected, but if you want to control the state of health, then you must go for these types of batteries like LTO, which does not affect their state of health, even at a high discharge rate. Right.
Sir, can we go for combining different characteristics batteries in order to obtain the various features required?
Uh, Usually it is not done because every cell has a different type of discharge curve. If you see, usually NMC batteries or NCA batteries, that voltage to SOC, there is a curve where the voltage and SOC is, I mean, it's a straight line of a curve. When you see a drop in voltage, the SOC drops, right? But in when it goes for LFP or LTO, the curve is not straight. So it is not recommended to combine a couple of different types of chemistries. You can alter their own chemistries to according to your requirement. So that's why I was telling about supercapacitors. You can use supercapacitors for sudden high discharge and fast charging, with paired with lithium ion batteries. That is being done.
Okay, sir. Okay, sir.
Okay. So shall we move on? Yeah. Okay. So these are the physical forms of the batteries. Typically, we have cylindrical cells. That is, the first one is 18650. That's the dimensions of the cells. That's why these kinds of names are put on their names. So 18650 is the first cell which has 18 mm of diameter and 65 mm of length. That's why it is called 18650, 1865. Then comes 2170, which has 21 mm of diameter and 70 mm of height. Then comes 4680. This 4680 cell is also made famous by Tesla Motors. This is also made in India right now by Ola. They call it the Bharat cell. This has different chemistry. They have invented their own chemistry, but the form factor is 4680. Then comes the if you can see the bottom diagram, these are typically three types of cells that we use, which has one is cylindrical cell that we discussed in the on the top. Then comes the pouch cell, or we call it the polymer cell, where the all the layers of cathode, anode, and separators are um, joined together, and it doesn't come with any safety features. So if you want safety features and a square or a cubical form factor, then you will have a prismatic cell that is written on the right side, that is shown on the right side in on the bottom. That prismatic cells are now typically used in higher capacity applications like BSS, or even some electric vehicles are using these types of batteries. For taking these prismatic batteries further, you will achieve something is which is made very famous, that's called a blade battery by BYD. You might have heard. This is just a prismatic battery with a different kind of form factor, which is extremely safe under extreme conditions like a puncture of the battery or some thermal runaway situations, which is extremely safe prismatic cells. So these are typically what is available in the market, these types of cells. So how cells are manufactured is we'll just cover briefly. Uh, Usually slurry is manufactured. Slurry is then coated upon the separators, layer of separator. Then calendering happens. After calendering, we go for cutting according to the size. Then cell is assembled, and then the electrolyte and other things are injected. So this is a very critical and very energy consuming process. That's why even we in India, even though we have lithium ores, these process takes a lot of energy, lot of capital investment is there. That's why typically we import the cells till date, and that's why we don't make cells. And also the slurry preparation, the name sounds very simple, but it's a lot of accuracy that takes place before the slurry preparation and finding out the ores. Usually we say that lithium is available in India, let's make batteries, but typically we use only 3 to 5% of lithium, and a lot of other nickel, manganese, cobalt, copper, steel, those kinds of materials are more required in the batteries, which we don't have a control of supply chain in India. So that's why we are not making cells, but hopefully within, like, let's say within a 3 year span, we'll be very self-sufficient in terms of lithium cells. So let's, as we discussed, these parameters are something that we need to consider in terms of our study. Typically 3.2, 3.7 voltages are there. Every chemistry has different voltage, different nominal voltage, different full charge voltage, different deep discharge cutoff voltage. So typically the lithium ion or NMC or NCA, these have 3.7 volt as a nominal voltage. They charge up to 4.2 volt safely, and they discharge up to 3.2 volts. So these factors you have to have from the cell manufacturer in order to design your battery management system circuits. If you want to design a good battery, you must know what the safe voltages are, and how you can charge or discharge the batteries, how much you can charge, how much you can discharge without harming the batteries permanently. In lithium ferrophosphate, you have 3.2 volts. It charges up to 3.65, and it discharges up to 2.65 voltage per cell. So accordingly, you will have to design the batteries. If you want a 48, let's say if you want a 48 volt battery pack, then typically you have to use 15 cells of lithium ferrophosphate, or if you want to make the same 48-volt battery pack in NMC or NCA, you will have to use 13 cells in series. So these types of calculations you must know in order to design a good battery or design a good battery management system. Also the capacity changes according to their requirement, that you might know. Then there comes internal resistance of the battery. Typically it is assumed that less internal resistance is better. Do you agree? Can anybody explain me what internal resistance might have a role of in terms of battery design or battery? What will happen if the internal resistance is more? Anybody?
It affects the charging, sir.
Yeah. Excellent. Anything else? What happens if you put a resistor and supply it directly to the resistor? It warms up, right? It heats up. So the same happens in cell also. If the internal resistance is higher, the cell will warm up while charging and also while discharging. So that heat generation is a loss. We don't want larger losses. That's why we shifted to lithium ion. Typically in other batteries there used to be a very much of heat and that's why a lot of losses took place. So lithium ion batteries have excellent internal resistance, typically from 5 to 7 micro ohms. A good cell has if you want higher discharge, you must have a very less internal resistance of the cells. Then you might know SOC and SOH, state of charge and state of health, that needs to be defined. Every cell has a different type of curve. Every chemistry has a different type of a curve in terms of SOC and also SOH. Every cell comes with a different number of life cycles, and usually what happens is when we are predicting the life, we are saying that life cycles are usually presented by a manufacturer. Someone says it has a 2000 life cycle, someone says it has a 3000 life cycle, but you must ask at what SOC, right? So typically it is said at 80% of SOC. Like if you discharge 80% of the battery multiple times, you can achieve it 1500 times or 2000 times. That's how the battery's life is defined. Typically if you reduce the SOC, like if you charge and discharge the battery within a 50% of state of charge, you don't charge it to full and you don't discharge it to full, you just keep upper 25% and lower 25%, it gives you twice the life. That's why a lot of vehicle manufacturers are also mentioning the usable capacity of the batteries, right? Our vehicle has 30 kilowatt hour of battery, but the usable is 25, right? So that's how they are managing their state of health of the battery. In order to give you maximum life, they are sacrificing some of the range of the battery so that they can achieve a longer life, like 7, 8, 10 years of battery life in the vehicle, right? So so these types of combinations are happening while assembling the batteries, like 3.7 and 3.2 volt batteries, and it changes according to the ampere hour requirement. Also charging discharging cutoffs are also different, that we discussed. Typically while assembling the batteries, what we do is we group the batteries according to the first of all according to their capacity. Then what comes is we assemble it. Before assembling, we typically assume, or sometimes we after grouping the batteries with capacity, then it comes to a discharge curve. So what we do is if some 10,000 cells are there, Then we randomly test a few cells for their discharge curve, and it is expected of the cells to have the discharge curve equal to each other, of equal voltage. So that's how a battery performs very well without any losses. And then we go for internal resistance testing, and then we go for voltage testing. Yeah, anybody had a question? I think someone raised a hand. I'm not sure.
Sir, you have changed the slide.
Sorry.
Slide has been changed. It
Yeah.
is at types only. Yet that's why I'm asking.
I'm seeing assembly. Are you seeing the assembly?
No, sir, I am not seeing that. That's why I asked. Let
Mm.
me rejoin again, and if that is the
Yeah.
case.
Please,
Okay.
please. I hope everybody is seeing assembly, the slide of assembly.
No, sir.
Size shape.
Uh,
Types.
Now?
Types.
Sir, please sharing your PPT, sir, please.
Okay. Now?
No, sir.
No, sir.
Wait. Can you see this now?
Sir.
Yes, sir.
Yes, sir.
Assembly,
Right? Okay. So I think you're stuck on this slide.
Types.
Yeah. So after that we covered the parameters, and then we jump to assembly of the batteries. Right?
Sir, there is some background noise.
Yeah. Wait. All right. Yeah. All right. Am I audible now?
Yes, sir. Audible.
Yeah. Okay. So where was I? So while assembling the batteries, while designing those battery packs, we covered what we consider as the parameters, like the chemistry of the battery, the typical voltages of the battery, how we can design the battery according to the voltages and AH capacity that is required. Then we covered how we do the grouping of the cells. So similar chemistry has to be there, similar voltage has to be there, similar voltage graphs of SOC has to be there. Then we come to voltage sorting, and then we sort according to the internal resistance of the cells, which all these parameters have to be similar of each and every cell of the battery in order to make a good battery. Okay, so while assembling them physically, we have a different types of methods that we use. Typically, according to the requirement, we can design the laser type of welding. Depends on how much area that needs to be connected with the cells, according to the current requirements of the battery, right? So if we need less current, then the surface area that is connected to each other's the cell to the connecting material, that is typically less. If the current is higher, the surface area will be naturally larger. So that kind of a but while doing this, we have to consider a lot of other parameters as well, like it doesn't need to be just according to the current. It needs to be sturdy while transporting. It needs to be it need not heat up while welding, and also while charging and discharging. So all these parameters have to be considered. Typically what is used is nickel strips or copper clads that is used to connect the batteries within themselves. As you can see in the on the left side of the bottom left, is it visible? Laser welding can all of
No,
you
sir.
see?
No, sir. No, sir. No, sir.
Which slide are you seeing? Method of assembly?
Assembly. Assembly only.
Oh my God, what is happening now?
Sir, the PPT is not
No, sir.
visible.
Okay, wait. Now? Are you saying methods of assembly?
PPT is not clear, sir. Just okay. We are not see this text. It is not possible to see this text. What are written on that?
Sir, please share the screen. Okay, I think you share the window.
Okay, okay. Wait.
Window.
Is it
Yes,
visible
sir.
now?
Visible, visible.
Great. So, where was I? So, if you can see on the left hand side, these are the types of laser welding. The circular type of thing happening on the laser by the laser. That type of welding is done where there is high discharge and higher accuracy is required. Uh, in the picture, you can see it is done on a prismatic type of a cell where higher discharge, more than let's say 100-120 amperes of current is required typically. That type of welding is used. After that, in the middle, you can see uh, tap welding, which is used commonly in India for solar applications or for other milk and other equipment manufacturers use these types of small machines to assemble these kinds of cells. Typically, it is used for NMC and LFP cells. And on the right hand side, you can see a different type of design of typical laser welded cell. So these types of cell welding is designed according to what type of current is required out of that cell. And it comes in a lot of other materials as well. Like I mentioned, we use a lot of nickel strips, which do not corrode with weathering, and also a few of you for higher currents, and even for prismatic cells we use aluminum and copper strips. Then let's come to BMS, battery management system. Uh, I hope the slide is visible of BMS.
Yes, sir. Yes.
Yeah. I hope while before jumping to BMS, does anybody have a question regarding the assembly and any other things that we covered?
Sir, when we are connecting cells in series parallel, is
Mhm.
the balancing voltage techniques are employed?
Yeah, that's why we use grouping of the cells. Balancing is typically used where the cell quality is not good. If you have to balance the battery while assembling, then you're made a big problem. You're in a big problem. The cells have to be of equal voltages, equal internal resistance, equal capacity.
Now, if the age of cell is okay, means life decreases, then characteristics may change. Under that condition, is there will be possibility of cell balancing required under that condition?
After this battery is used for, let's say, 3-4 years, maybe
Hmm.
we can do balancing. But typically for a new battery, when we are designing a battery, then we must take care of the equal voltages, equal capacity. And one thing is there, like if you want to connect cells to each other, then the definition or the resolution of voltages, current, voltages, capacity, and internal resistance has to be very high. Like you cannot connect a multimeter and say 3.2 volt cell is there. You have to go at least 3 digits after your decimal point, like 3.111. Every cell has to 3.111. The higher your resolution of your reading, the better the chances of the battery surviving a lot of years.
Okay. Okay, sir.
Right.
Thank you.
I hope I answered your question. Yeah. Any other questions regarding assembly? All right. So let's move on to battery management systems. I think a lot of you guys is from electrical and electronics background, or all are shared.
Yes, sir.
Okay. So you might have you might be familiar with battery management systems. Typically, what we use in the industry comes with these types of protection circuits that we call. It uses different types of MOSFETs to cut the power or allow it or not allow it. Usually the features are over protection, over discharge protection, over current protection, short circuit protection, and reverse polarity protection. These are like very basic protections that we expect out of a BMS. Uh, as you can see on the screen, the typical flow of the logic. And there are three pictures of the BMS. First, left hand side is a very basic BMS. This is a 4 cell combination BMS. On the BMS, you can see on the top side there are available the connections from B plus to B negative. We can connect all the cells to those spots, and you can see this is very basic BMS that is used for very small applications where the cost effectiveness is required. Then comes the bottom left BMS, that is a high voltage master BMS, and on the bottom right you can see a slave BMS. So what happens for a larger battery pack, typically from a 800 volt or a 600 volt battery pack, you must go for the slave and master architecture of a BMS, where small battery packs of, let's say, 48 or 36 volts are made using slave BMSs, and those all slave BMSs are connected to a master, like we can see on the left hand bottom side. The master you can reprogram, you can connect to different types of systems. If you have SCADA, you can connect it. If you have LAN system in your application side, then you can use that. You can use UART or CAN communication just to get the information about the cells, the temperature of the cell, the voltages of different types of cells, the SOC, SOH of those kinds of parameters you can get out of the battery using these master BMS. All right. So why are we using battery management systems? Is first of all, the largest is because of monitoring. The battery has to be monitored. All the parameters of battery has to be monitored. The log of those parameters has to be kept somewhere for obviously for our own knowledge and advances for advances of the same applications. We typically monitoring is one of the very widely used application of the BMS. Typically, other like control and protections are not as important in terms of customer feedbacks. You have to for controls and protection, as I'd said in the early slide, we use overcharging, over discharging, short circuit protection, reverse polarity protection. Those types of controls and protection can be used in battery management system. Then as you all know, I think this is a very common topic of study right now is SOC and SOH, and the effects of temperature of on SOC, the effects of temperature on SOH, and obviously event log. If something fatal or something catastrophic happening, the event has to be logged, right? So we discussed a lot of parameters like voltage, internal resistance, and all the parameters we discussed a lot. Can anybody tell me what it will affect, what the effect of internal resistance may happen on SOC? What happens if the SOC, what happens if the internal resistance is higher? Then what happens to SOC? Will it change or will it remain the same? Okay, forget. What happens if the temperature of a battery rises? Just one sitting battery, one is at 20 degrees Celsius, another is at, let's say, 50 degrees Celsius. What will happen? Why do we need monitoring? Anybody? See, usually batteries are very notorious. They are very sensitive to each and every parameter, right? So let's answer the question first. If the temperature of the cell rises, typically internal resistance also rises. If internal resistance rises, the battery will start discharging on its own. The shelf life of the battery will also decrease. The SOH, the health of the battery, will also decrease. So that's why a lot of batteries nowadays come with their active cooling system. You might have heard a lot of marketing thing is also happening for active cooling batteries, right? In a lot of electric cars, they are using active cooling as well as active heating for the battery to remain at a constant temperature of, let's say, 15 to 20 degrees Celsius, or whatever the manufacturer of the cell has recommended, right? So these types of that's why we need all types of monitoring. We need a lot of protections just to make sure the battery performs as we have designed it. The safe operation of the battery is ensured, and these are the advantages of the BMS. That's why we use the BMS. So I think as I hope you can see the screen, the BMS connections. Hello.
Yes, sir. Yes, sir. We are seeing the block diagram of this.
Yes, sir.
Perfect. So typically the upper side display is what is of the master, and the small four circuits that you're seeing are typically the slaves of the battery, right? So slaves are interconnected, and it is all the information is fed to the master. Then master typically has all the information from the slaves plus the current of the battery that is charging or discharging at, and then comes the relay. This is a very simple basic BMS that we use under my master and slave architecture, where the master decides to continue to charge or discharge with the relays. This is very primitive BMS. These types of BMSs now are not used in the industry, but this is for our purpose. It is very simple to understand, where we we monitor each and every cell from the slave BMSs, and the information is fed to master BMS. This information can be collected using CAN communication or whatever your requirement is there according to your application. All right. So before going for testing, does anybody have any questions about battery management system, BMS?
Sir, is it a very simple battery management system, which is a older
Yeah.
version, or it is AI based?
This is older version.
Okay.
For
Go-
AI based, you can connect this from to your application so that you can process the data using AI.
Okay. Okay.
Right.
Okay.
AI is not working with the BMS. AI will process the information that the BMS provides.
Okay.
In these types of BMS, typically what is done is this BMS is connected to some system of the application, and the application system gets data from BMS like cells, cell voltages, cell temperatures, cell SOC, the way it is charging and with the way it is discharging. And the typical graph is also can be collected from this BMS, and then this data can we'll process with AI or ML or whatever you want to do. First of all, we have to have data. From battery side, you have to have maximum data to feed your AI model. Then only the predictability of AI will be important, right?
Okay, sir. Thank you.
Yeah. Anything else? All right. Then comes the most important part, testing of the battery. Usually we go for at least a couple of major testing, which is capacity versus SOC. This is a very simple diagram of what we are typically using for smaller applications. These types of machine give you a curve of discharge, how the battery is performing under different types of loads, also different capacity of loads. Like different types of load, consider inductive load or resistive load, and different types of different amount of load like 10 ampere, 50 ampere, 30 ampere applications. Yes.
Hello, dear participant, please unmute the mic. Dear participant, please mute the mic.
Okay. Where was I? So testing. So which is very important. Typically we go for various types of testing, but minimum we do capacity testing as per the applicant's requirement. So for example, for electric rickshaws, e-rickshaws, we go for 20 amperes of continuous discharge, and we measure we monitor the SOC graph according to the voltages, and we also make sure that the both the charging and discharging cutoffs are happening as per the design. Let's say for a typical 60 volt battery, the for LFP, we consider the maximum charging voltage of 69.35, and the complete discharge battery is typically at 52 volts. So we make sure that the accuracy of cutoff voltages is there, and we get the full capacity of the battery accordingly. If we are designing a 100 ampere hour battery, then we must get a capacity of 100 or 100 plus 102 ampere hour. And sometimes if the customer is having a requirement of SOH, then we go for full life cycle testing. So we test it for around 100 life cycles of the battery. We charge it and discharge it. We completely charge the battery and discharge the battery for 100 times in a row, and we predict the graph according to the state of health of the battery after the 100 life cycles. We predict what will happen after 2000 life cycles or 1000 life cycles. These types of testing also happen, where we can see that almost we have in our industry have almost 1.5% of defects or uh, uh, that are detected in our own testing lab. So I think someone asked about balancer. So these types of balancer are used sometimes at these stations, but it is not recommended. We do not recommend to use these types of balancers just to fix the problem in hand and not having a life. If we put a balancer, the same problem will happen within 3 to 6 months. So it is not recommended to use balancer, but some jugaad solutions happen, and uh, industry does not tolerate such types of practices, and you will not earn another award or any other orders from those types of customers if you use balancers. So, what are the fixes? If we found some defects, typically it's some manufacturing error like dry solder or some connection errors, the defects in that types of all types of welding that we have seen, we have covered it. Those kinds of defects may occur while testing. So typically the battery is again opened and whatever the corrections have to be made that are made and then again tested if the defects are removed or not. Again, for other some of the applications like some smart electric vehicles, we need to connect the load as well as the communications to the testing rig of the vehicle, so that the battery is performing as per the design of the electric vehicles, and it is also communicating whatever is happening within the battery. Some types of testing may also come under vibrational table. Some IP rating testing can also be done with this type of batteries. Typically for electric vehicles, we do these kinds of testing. Like we put the battery for on a vibrating table for 30 minutes, and even on the table while vibrating, the battery has to perform very well. After that, for IP67 rating, we take the same battery pack and submerge it in water for 1 meter, and for 30 minutes we monitor the battery, and after those two tests the battery has to give full capacity while communicating without any mechanical failure. These types of testing is happening for AIS 156 revision 2. If you know, for electric vehicles we have new rule of AIS 156 revision 2 since 2022. So these types of batteries testing is happening. This is a typical test report for capacity testing and SOC. As you can see, we mention all the depth of discharge, all the currents at which is this is tested. As you can see on the screen, I hope everyone can see the report, test report. Are you seeing the test report?
No, sir.
Is the presentation stuck again?
Yes, sir.
Yes, sir, please.
Yes, sir.
Yes, sir.
Okay, got it. So this test report comes under this 25.6 volt battery of 36 Ah, and we discharged this battery at 10 ampere, and as you can see,
Sir.
sorry.
Slide is not visible.
Yeah, okay. Wait. Now?
Now visible.
Yes, sir.
Visible, sir.
Okay. So this test report comes under this battery is 25.6 volts, 36 ampere hour. and we tested it at a 10 ampere continuous discharge. The typical load used is inductive load, and this is lithium ferrophosphate chemistry with 8 strings and 20 ampere of battery management system, which allows maximum current of 20 amperes. So these types of batteries typically we charge fully up to 29.2 volts, and the maximum discharge at 100% depth of discharge is 21.6 volts. So as you can see, a continuously 10 ampere load is given to the battery, and it came that 36.1 ampere hour of battery capacity that we have tested. And also for charging, we observe that similar thing is happening. The charging started at 21.6 volts. At 50% of SOC, it was 25.4 volts, and at maximum voltage 29.2 volt, where the battery capacity was 100%. And it is observed that while charging and while discharging, both the SOCs were typical. So typical, this is what is basic test report that I could share with you. Next. So I hope the slide is changed to standards.
Yes, sir.
Yeah,
Yes, sir.
okay. Perfect. So in India, these are the standards that we are using for each and every cell comes with a BIS certification. And the cell is tested under this BIS, and then after that only we allow the cell to come in the country. After that, the cell is assembled and the battery packs are made. As I discussed earlier, AIS 156 revision 2 is one of the standards for electric two-wheelers, which is very stringent, and I recommend everybody to study this AIS 156 because it is very well designed, and each and every battery has to be at par with this standard, because they test it for vibration, they test it for thermal shock, they test it for drop test, fire resistance, IP68 or IP67, water ingress, pressure ingress, thermal propagation. Each and every factor is tested. I highly recommend you guys to go through AIS 156. It is available on the website of ARAI, the Automotive Research Body of India. So I'll highly recommend you guys to go through if anybody wants to dive deep into battery testing and the standards of the battery in India. The same standards apply in a lot of other countries also. If there is any export oriented vision, then this standard also works in a lot of other countries. Also, in testing of these batteries, they abuse the battery very well. Like they take one. All right. They take one battery pack, they applies all the types of loads like fire load, drop test, thermal shock, vibration, water ingress, pressure valve testing. All the testings is done in on single battery pack. You don't get to have multiple battery packs tested for other applications, like one battery pack for drop test, other battery for IP68 or 67 rating. You get only one battery pack, and all the tests have to be done and passed on the same battery pack. Then for BESS, we have IEEE standard, which is also very vast, but if anybody wants, you can go on IEEE website and you can find all the standards. But for studying and typical applications study, I'll recommend the AIS 156 for all of you guys to study. Then if we discuss it further, the AIS 156, we have to have a smart BMS. In smart BMS, we have what typically a smart BMS is having a communication, like a CAN or a Bluetooth communication with at least 4 temperature sensors, one current sensor, one pressure sensor, and a buzzer if anything goes wrong, if let's say if the temperature rises above 60 degrees Celsius, the buzzer will start buzzing. I'm not sure if anybody has a old electric two-wheeler. Typically, I think for TVS iQube, the older version, they had a buzzer, and if you just loaded the vehicle and started the vehicle, it will start buzzing. And after, even if you continue after buzzing, then the vehicle would stop after overheating. So these types of protections and buzzers for your knowledge are typically used in the battery packs. Some of the battery pack come with GPS, some may not. But where there is swapping stations for electric two-wheelers and e-rickshaws, a lot of companies are employing swapping of the battery instead of charging, because the charging takes a lot of time. The battery comes with a GPS, inbuilt GPS, so that it is tracked where the battery is in terms of theft or protection of the battery. And also charging speed controls are also there in the smart BMS, where it does not allow it to charge rapidly when the SOC is very higher or very lower. Typically what we do is, if the battery is fully discharged, we go from 0 to 20% with a very small current, in order to in order to get maximum life of the battery, SOH of the battery. We charge it from 0 to 20% with a very less current. Then from 20 to 80 we charge it with maximum current, and again from 80 to 100 we charge it very slowly in order to achieve maximum life of the battery, to ensure that the SOH is typical. Right. So what are all the aspects that we need to consider while designing a good battery? Is typically the power and energy requirements are like the basic. Like for example, let's consider an typical electric rickshaw, the e-loader that we know in India, that requires usually 48 volt 100 ampere. So that is the basic parameters of the batteries that we have to know. Second, the consumption, the rated and maximum power of the motor or whatever the application is. Typically in e-rickshaw we have around 30 to 40 ampere of a rated current and maximum current of a 60 ampere. So that we have to know in order to design a good battery or a good BMS. Then comes with the physical parameters, like size and weight of the battery. What constraints are there in terms of size, or what constraints are there in terms of weight. Then comes other enclosure, wire, nickel, copper, whatever, the requirement according to the application. For example, for e-rickshaw that we discussed, we have to have at least 3 communication pins and 2 high voltage pins, right? So these types of applications, you have to know what you are connecting to. For UPS batteries, we just have to have 5 communication pins and 2 high voltage pins, right? So these types of things you have to know. And what type of communication you are using, CAN, RS485, or any other type of Bluetooth connection you need. These types of things you must know before designing a good battery or a good BMS. Then I hope everybody is caught up to this battery design. Does anybody have any question about battery design or the standards that we are using, or any other questions related up to whatever we have covered? Okay, so I shall move on. Battery recycling. This is one of the very challenging parts in India. Battery recycling is not happening right now. Very a small percent of batteries are getting recycled, shredded, and then might be some of them are exporting the raw materials that are shredded and segregated. But typically today's age is of circular economy. So in terms of recyclability, we can recycle more than 90% of the materials of the lithium ion cell. All are
Sorry, sir. Sorry,
Yeah.
sir. You are in which slide?
recycling.
Sir,
Sir, it
not
is not
changed.
visible.
Okay.
Slides
I'll
are
share.
not moving, sir.
Now,
Yes, sir. Yes, sir.
recycling. Yeah.
Yes.
Okay. Okay. Perfect. So as I was saying, more than 90% material can be recycled of the lithium ion cells or lithium ferrophosphate cells. In the typical diagram, you can see when the battery is manufactured and after the use, end of life, the all the cells are getting first the cells are separated from the containers or BMSs or segregated. Then the cells get shredded. And then after that, we recover electrolyte from it. Anode, cathode, foils, all are segregated, and typically all the cathodes can be reassembled using the technology that we discussed of cell manufacturing. Almost like more than 95%, I would say, can be reassembled into a battery pack. So uh, direct recycling of lithium batteries is very possible, although it's not a practice in India right now, but it is very achievable. It is happening in a lot of countries, and uh, when it will start in our country, we will see a great reduction in the price. Right now, lithium batteries are very high in cost compared to other lead acid and nickel manganese cobalt sorry nickel hydride batteries. But once this circular economy fits in our country, the future cost will be, I'm sure it will reduce to half. And if anybody is interested in any venture, future proof venture is this is a huge opportunity in lithium battery recycling, and also a large market, potential large market. Today, I'm not sure if the market is that big, but potentially in the future, I'm sure lithium battery recycling is going to be a big thing. All right. So this is from my side. I'm open for questions.
Sir, is there any methods to reduce the thermal resistance of battery pack?
Thermal resistance of battery pack, yes, by monitoring it continuously and actively cooling the battery pack, you can do it. Typically in electric vehicles, we are using glycol water or cooling thermal pads for uh, controlling the temperature of the battery pack. Typically a lot of EV cars are using active cooling systems just to maintain the temperature of the cells within the recommended range, let's say 15 to 20 degrees Celsius. If the outer temperature, environmental temperature is higher, let's say 40-45 degrees Celsius, the glycol water cools it down. Or if the outer temperature is less, like 0 degrees Celsius, snowfall, then the battery will heat it up. The system will heat up the battery, so to keep the battery within the range of what is recommended. I hope I answered your question.
Yes, sir.
Okay.
Dear participants, any question? Dear participant, any question in your end? Please unmute the mic and ask the question.
Hello, sir.
Yeah.
Sir, you have shown the BMS. Okay.
Right.
Huh. What all it is doing, sir? Then we are thinking of doing the cell balancing and other things,
Okay.
like a measurement of SOC, SOH, etc.
Right.
And
Right.
health of battery. So, but
Right.
what about yours, sir? What it is doing actually?
We are doing this only the monitoring of the cells. All the SOC, SOH has to be defined by some other type of processor or a microcontroller. This the basic BMS I showed. This has protection systems and monitoring systems. We monitor the cell temperature, cell pressure, cell temperature, cell voltages, and the current that is giving. And in terms of protection, we are giving short circuit protection, reverse polarity protection, overcharging and over discharging protections of each and every cell. Each and every cell is monitored and protected for overcharging and over discharging in terms of voltage.
And what I would like to know, sir, this set of this BMS, does it come along with the battery you are providing as a
Yes.
battery bank that you are providing?
Yes. Each and every battery pack that we manufacture comes with a BMS. Without BMS, we do not ship any battery pack.
Okay, sir. Okay. Thank you.
Typically, what happens is we ask for a battery pack energy solution. Like what is your requirement? Like if you want to make it big, make it small, you have a very small cabinet, or you have a high discharge rate, or you have a very economic battery, or you can spend a lot. Typically, those are the parameters which we consider first, and then we go for a solution, like what types of cell is used, what type of BMS is used.
Okay, sir. Thank you.
Okay.
Any question in your end? Okay. Shall I conclude the session?
Sure, sir. Sure.
Okay. Thank you, sir. On behalf of Electrical Engineering, Decades Textile and Engineering Institute, and ATAL FDP, I would like to thank today's expert speaker, Mr. Chinmay Gore, sir, for his insightful session on battery management system, battery production system, and basically balancing. Okay, this is a valuable session. Thank you, sir. And
Thank you.
today's session is over. Magdum, sir. Participant, please join
Yes,
us.
thank you very much, Gore sir. Thank you very much.
Thank
So